Okay. So quiz Dodd from Perimeter will tell us about quantization, reduction mod P, and autoequivalences of the Weyl algebra.
Okay. Well, thank you so much for having me. Okay, yes. As the title suggests, I'm going to be talking about autoequivalences of the Weyl algebra. So I should start out by telling you what I mean by the Weyl algebra and why one might be interested in what its autoequivalences are. So as a non-commutative ring, the Weyl algebra has a very simple presentation. I'm going to denote it dn of C, and it's simply the non-commutative algebra, which has two n generators, which I'll denote x1, xn, d1, dn, and relations which look as follows. di bracket with xj is Kronecker delta ij, and the di's all can be as do the xi's. All of these relations are for all ij. So, it's sort of like a polynomial ring in two n variables, except it's a little bit non-commutative. And what it is supposed to be, what it actually is it's the algebra of polynomial differential operators on an. So this is the algebra of polynomial differential operators on an n-dimensional complex affine space. Okay, so a typical element of this algebra, P, is going to look like, so the elements look like P is equal to sum over some multi-index I, xn, and then, d1, n. Okay, so where this fi is supposed to be a polynomial. So this is in okay, and the multiplication looks like multiplication of differentials and functions. So, these di's are supposed to be partial xi, right? So they commute with each other, but when they act on a polynomial, they act by this relation, which is that your differential operator differentiates the polynomial. Okay, so that's what it is. So it's a sort of very algebraic version of something that's supposed to be telling you about linear Pde, right? So a typical element of this algebra is like a linear Pde here. And in fact, this algebra and modules over this algebra really do have something to do with linear Pde. So, so to any such P, I can associate the module, the dn module, M, so P, say, which is just, you take the algebra and you mod out by the left ideal generated by that element. Okay, and that module is some kind of algebraic incarnation of this differential operator. So, for instance, what do I mean by algebraic incarnation? So let's suppose that you have P and Q in Dn, and you have M sub P isomorphic to M sub Q as Dn modules. Is this too far over? Can people still see this? Okay, great. So let's suppose that two of these things were isomorphic. This implies actually that the equations, the differential equations, P equals 0 and Q equals 0, have isomorphic solution spaces. On each open subset. Of Cn. So the actual analytic solutions are the same when you restrict it on any open subset of the space. Well, they're isomorphic as C vector spaces in a natural way. The same is a little bit questionable, but they're equivalent in some very strong sense. So from a differential equation, you go to a module, and that module is somehow telling you important things about the differential equation. It determines, in some sense, its solution space. And let me say that you can do this for systems as well. So I won't write it up, but to any finite system of linear Pde, you can also associate a dn module, and a similar property is true. So similar. Let me just make a remark, without writing out For a matrices, let me remark that systems of PDE, of linear PDE. I don't know how many PDE people there are in the audience, but I've been called out by saying PDE when I mean linear PDE before. For analysts, that's like very offensive. For me, I only work with this algebra, but I should be careful. So anyways, for systems of linear PDE can also correspond to D modules. And we have a similar property where the module is telling you about the solution space in some strong way. Okay, so it's an algebraic incarnation of some important facts about these linear PDE. And if you thumb through your textbooks on classical analysis, what you'll see is that there are some important invariants of a linear PDE that you might want to look at. In particular, the one that I want to talk about, that I want to sort of mention here, is its wavefront set, or also called singular support by algebraists. Okay, so to any linear PDE, P as before, you just keep the same one, you can associate a set. And in this case, it's actually an algebraic variety. Inside, not Cn, but C2n. Okay? And this variety is called, so I call it the singular support of P. You also hear wavefront set in the analysis textbooks. And what this singular support is, well, it's pretty easy to define. So let's keep the equation for P up here. So if you have a P like this, what you do is you say, okay, I have a sort of ordering on my differential operators by the total degree. Okay, so to such a P, I associate, so to P, I can attach the expression sum over I, such that the total order of I is maximal, and then Fi and Di. Okay, and you see, you might be worried if you look at these expressions that you're allowed to change orders of things, but if you look at the relations, which I've conveniently just erased, what you'll see is that the di's and xi's don't commute with each other, but their commutant produces something that has lower order in D. So that's a little exercise. So in fact, this highest order term is sort of well-defined, regardless of how you present this P. So you can check that this is a well-defined operator, okay? And so now this is just, it's a well-defined operator in xi's and di's. So let me just conveniently rename these things. So this goes to I maximal. So let's call it now Fi of x, and now just y1, I1, yn. So to indicate that x's and d's now are supposed to commute with each other, let me rename the d's y's. And now this is just a polynomial in x and y. And it turns out that this doesn't depend, for the reason I indicated a second ago, this doesn't depend on the order in which you presented P up here. So you can take the zero set of this polynomial, sum over I, over my maximal f of x, y. So this is a polynomial in 2n variables, so this has a zero set inside C2n, and this is the singular support. Okay, so if you haven't seen this notion before, let me say what it looks like just in the case of a one variable. So if this seems unfamiliar to you, let's consider just the one variable case. So here, I just have ordinary differential equations, and with polynomial coefficients. So it's going to be an expression that looks like this. Okay, so in this case, the polynomial that I would attach, well, the order is just the powers of, in powers of D. So I kill all the lower order powers of d, and I just attach the polynomial Pnx times y to the n. And so now the zero set of that polynomial, the x and y, are the colors. Okay. So the zero set of that polynomial looks like just y is 0, maybe counted with multiplicity n if you care about multiplicities, and then some vertical lines which corresponds to the zeros of Pnx. So these points are zeros of P. Okay, so in the world of classical ODE, I mean, what this variety is telling me is exactly where this ODE has a singular point. Right? So if you go back to your Fuchs's theorem or your other classical ODE theorems, there's some finite set of points in the affine line where the ODE is, it blows up. And those are exactly the points that correspond to these vertical lines here. So this is the reason for the name singular support, because it's telling me something about singularities of differential equations. So this general business is just a higher dimensional version of that. Of course, the varieties will be a lot more complicated, but at a fundamental level, is there a question or? Oh, sorry. At a fundamental level, where these varieties are telling you something about where this differential equation or system of differential equations is going to degenerate. And it is a fact that this algebraic variety that I've constructed here is an invariant only of the associated dn module. So remember, I told you how to construct something to a differential operator like this, but in fact, to any m, a dn module, I can associate this SS of m, okay, and it's well defined. So in other words, if I have MP, I shouldn't say n, I should say so. If I have MP is isomorphic to MQ from before, then in particular the singular support of P is equal to the singular support of Q. So again, the module over dn, you want to work with the equation to write things out, but it turns out that the module over dn is sort of the fundamental home for these kinds of invariants. If two equations or two systems of equations have the same module, then they end up with the same singular support. Okay, I won't prove that here, but it's sort of an exercise in filtered rings, if you like. So what's happening is that this dn has some sort of order filtration based on the orders of differential operators that are appearing, and when you take the associated gradient of that filtration, you get a polynomial. That's a sort of more high-tech way of saying this, the fact that this thing is well. So if you like... Oh.
Isomorphism doesn't give isomorphism, it gives just exact identification.
These are the same variety. Yeah, that's right. They're just the same set. And if you like multiplicities, they even have the same. They're even the same cycle. Mm-hmm. So I won't get into that too much, but to each component of this variety, you can assign a multiplicity, and even that will be preserved. Okay, great. So this is sort of an algebraic retelling of an old story. And it's a good story. I mean, these singular supports tell you a lot of interesting information about systems of linear Pde and about modules over this ring dn more generally. But there are some not great features to this singular support construction. So this SS has some drawbacks. Okay, so I'd like to highlight two of those drawbacks. So the first drawback is that it's not a very refined invariant. Not very refined. So what do I mean by that? Well, even if we just take a glance back at this case, what SS was telling us was that if you input into it a linear ODE here, what you get out is essentially some finite set of points in the plane, maybe with some multiplicities. Now, if you have two ODE and they have the same singular support, it essentially tells you that they have the same order and their singularities are at the same spot. But if you know about classification of ODE, then when you start to think about this, you realize that this really isn't telling you all that much. I mean, it's great for what it is, but for instance, if I take that affine line and I puncture it finitely many points, the ODE, which have singularities at those punctures, they're sort of in bijection with representations of a free group, right? You have a monodromy representation. So let me say, to an ODE, I can associate its monodromy representation. So that's a representation from pi1 of A1 minus the singular points to map from that group to GLN, where the n is the order of the differential equation. And that's a lot of stuff, right? I mean, even if you fix the singular points and you fix the n, you're still looking at representations of a fixed rank of a free group. And that's sort of a wild problem in mathematics, I think, right? I mean, you don't really have any hope to try to say all that much about that except in special cases. So this is telling you that if all you know about an ODE and of course, in the higher dimensional case, things will only get more complicated. So if all you know about one of these things is a singular support, you really still have a big zoo of potential things that it could be. I mean, you're not really very close to telling what it is. So that's one sort of problem with the singular support. As nice as it is, you really would like to try to classify ODEs in a more refined way. Okay, and there's a second problem, which is interrelated. And this problem is that this singular support doesn't behave very well with respect to certain natural operations. So the singular support is not very natural. I'll sum that up by saying not very natural. I'll put natural in quotes. So we'll get more precise as we go on. But what would you mean by not very natural? Well, here's an example. Again, just even looking at the world of ODE, there's a very nice involution, let's say, on the set of ODEs. So to any ODE, we can associate its Fourier transform. In other words, I have some expression here, which is polynomials in x and d. And to that, I can take an operation, which is x transforms to d, and d transforms to minus x, right? So we can apply this involution on this space of things. And this will take one ODE and it'll spit out another, right? So this takes, well, yeah, it's an involution. There's an involution. Or no, actually it's not quite an involution. You need to do it 4 times to get the identity. Sorry, it's I don't know what to call it. Half involution? Tetra? I don't know. Anyway, it's a nice operation. If you do it a few times, you get back to 1. So it's a half involution on the set of isomorphism classes of ODE. Let's just say on the set of ODE for simplicity. And of course, it's extremely useful, right? I mean, being able to transform an ODE is one of the main ways that you can try to solve them and try to do things with them. So it's not great that our invariant here, this singular support, doesn't behave very well with respect to Fourier transform. But that's the case, right? If I swap x and d, this singular support, it depends on an order filtration, which is an ordering in the variable d. So if I switch the variable d and x, that filtration goes askew, right? There's the whole idea of an order of a differential equation and its leading term are not at all preserved. Right? So this operation.
So you're not applying the Fourier transform to the equation, just to the variables.
Well, I mean, right. I mean, what this operation is doing. I mean, I'm taking the ODE that the Fourier transform of a solution satisfies. Essentially.
I see.
Right. So right. I mean, if you imagine solving these things on some little open disk, and then you hat the set of solutions, those will also satisfy linear ODE, which is this one. So that's what. Yeah. Okay. So the point is, since the singular support depends on the order in D, on the powers of D, let's put it that way. It'll go haywire into this operation, right? So it will go haywire. It's hard to compute under. Okay. So that's what I mean by not very natural. There's some very natural operations, in particular something like Fourier transform, which this thing doesn't seem to preserve, and it doesn't preserve. Okay.
But why do you consider the Fourier transform natural in this setting? I don't see how it's natural.
So I mean, I'll make it precise. Essentially, what I mean is that if you do this, this change of coordinates defines an automorphism of this ring D1. And anytime you have an automorphism of a ring and a module over that ring, you can make a new module. So that's what I mean by natural operation. Yeah. Okay. So I'll get into it in a second. Okay. Okay. So so in fact, both of these problems sort of stem from the same source, which is exactly what your question is pointing towards. And the source is that in order to define SS, we had to pick a basis in the algebra. So both problems are because we picked a basis. We chose x1, xn, d1, dn as a basis of this algebra dn. Right? So in both cases, the module, of course, is the module, regardless of in what basis you compute the action, right? I mean, that's just a general principle. But so any invariant that you make up, which is going to depend on choosing a particular basis and how it acts, is automatically sort of not going to be a very refined and or natural thing. But it's going to naturally lack a lot of power. And so what these things sort of suggest is that we should be trying to look for invariants that are somehow basis independent in some sense. So what we would want is just to attach invariants in a sort of coordinate free way. So we want to attach invariants to dn modules in a coordinate free way. Okay. So in order to tell you what that's really supposed to mean, I have to tell you what the automorphisms of these algebras are supposed to look like. And in particular, I'm going to start in the case n equals 1, where it's sort of understood what these words natural are supposed to be.
I'm sorry, I just forgot.
Sure.
When you introduced this singular support, I mean, I know why I care about singular
Sure.
support. But I was wondering why you motivate. I mean, because it looks like it's not doing anything you want. But why did you? I mean, for me as an analyst, it talks about regularity issues and microlocal analysis.
Yeah, sure. No, it does that for me as well. I mean, the reason we introduce it in algebra is, I mean, at heart it's the same reason. I mean, namely, we want to know, whether our modules are polynomial, how overdetermined our systems are, and yeah, exactly as you say, we want to know where there are singularities and how bad they are. So in a sense, it's the same suite of issues. I'm only attacking this thing. Yeah, maybe this first part of the talk is a bit of a straw man, but I mean, I don't want to say that it's not a good invariant. I mean, certainly it does a lot for you. I only wish to highlight some features of it that maybe are not pleasant. But you're right. I'm sort of brushing over the reasons that it's good. I mean, one thing that's great about it is that this taking these monodromy of ODEs is great, right? You really want to know where your ODEs are singular, whether or not they have regular singularities, and those are all things that we want to know from an algebraic perspective as well. So for the same reason that you care about it in ODE, you care about it for DN modules as well. Yeah. So it's not to say that you shouldn't consider it. It's just to say that it has certain features that are lacking. Yeah, that's right. Okay. So all right. So let me tell you now about automorphisms. So the first thing that suggests a way to fulfill this want is an old theorem of Dixmier from the 1950s, I want to say. Late 50s. And the theorem says this. There exists an isomorphism, capital T, from the automorphism group of D1 onto the automorphism group of, okay, so here my algebraic geometry is going to come out. So this A2C is just, if you don't like this notation, you can think of it as just an affine plane. But this is to indicate that I want polynomial automorphisms from the plane to itself. So I don't want to allow holomorphic or any other kinds. And the subgroup where the Jacobian is 1. So this is the group of automorphisms of this ring, D1. This is the group of polynomial automorphisms of the affine plane, whose Jacobian is everywhere equal to 1. Right, so if I take the Jacobian of an automorphism of the plane, it's automatically a constant, because it's some never-vanishing polynomial. And so I want the subgroup where it's always 1. Okay, so this is a nice, well-defined group. And what Dixmier shows is that aught D1 and this automorphism group are actually the same. Okay, so this immediately starts to suggest things about, well, what do we mean by a natural invariant? So why should these two things be equal? So his proof is completely computational. So the proof is quite computational. But I can give you the highlights, which are pretty nice. Essentially, the highlights of the proof are that he just tells you things that generate both groups, and then he just sort of shows you how to set them equal to one another. It's quite hands-on. So the first thing he says is he gives generators for both groups. Actually, generators in relations, but he gives generators for both groups, and here's how they look. So inside each of these groups, there's a copy of SL2. So we have SL2C. Well, it acts on the complex plane just because it is a thing that acts on the complex plane, just by definition, the natural action. And then he says that there's also an embedding of SL2 into aught D1. Now the reason is that, D1 is an algebra and it's got two generators. So you might as well just let SL2 act on these generators. So you let SL2 act on the vector space Cx plus Ct, right? This is a vector space that generates the algebra. If I take a linear automorphism of this vector space, well, the only thing that I have to check is that it still generates the only thing that I have to check is that this linear map is an algebra automorphism, right? So it's obviously, you can obviously make any automorphism, but in fact, you can show that if phi is any element of GL2C, then phi of D bracket phi of X is equal to the determinant of phi dx. Okay. So it's an exercise in calculus. So in particular, if phi is in GLN, then it will be an algebra automorphism of D. Oh, sorry, if G is in SL1, SL2, excuse me, it will be an algebra automorphism of D1. There's a lot of different indices floating around. Unfortunately, there'll be more later on. Okay, so there's your SL2 acting on both sides. And then he says, well, there are more automorphisms of both of these things than that. So in addition, we have the following groups. So we have the following automorphism of A2. You can take X to X, and you can take Y to Y plus F of X, where F of X is any polynomial. Just CX, anything. So this rule, the inverse to this is just X goes to X, Y goes to Y minus F of X. So that defines an automorphism of A2. And then he says, well, I can write down an automorphism of D1 that looks darn similar. Namely, we also have X goes to X, and D goes to D plus F of X. this thing brackets with x to 1, right? Because f of x bracket x is 0. So it's easy to check that this is an automorphism of D1. So he just writes down some families of automorphisms, and then he says, he does some hard computations, which I'll skip, but then he says, hey look, these generate the whole loops.
That's actually a theorem of Jung from like 30s.
Oh, is that really? Even in this form?
Yeah.
Oh wow, I didn't know that. Okay. So I first read about this theorem in a paper of, so the first proof I saw of this was the 80s in a paper of a mathematician called Makar-Limonov. And then he references Dixonet's paper from the 50s. So you're saying it's actually even older. Oh wow, okay. I feel bad now. You said Jung?
I think J-U-N-G, if I remember correctly.
30s.
Yeah.
Okay. Well, that even underscores. I mean, it's a very elementary.
No, just this part. Just the odd A2.
Oh, the automorphism of A2, but not the D1 part.
No, I don't know.
Oh, okay, yes. Yeah, that I believe. Okay, great. So the fact that these two things generate,
Yes.
for A2 you need, if you want all of A2, you take GL2 and these. If you want the Jacobian 1 ones, you take SL2 and this. But at any rate, okay, that I definitely believe. I believe that's older, yeah. Yeah, but the point is it's completely, and I'm sure his proof is elementary as well. I mean, all of these proofs are just completely endless. Okay, so it looks a little bit miraculous, but at the very least, it gives us some sort of hint as to what a better theory of cycles might look like. Okay, so if we believe this theorem, and if we believe that this isomorphism is sort of a unique natural thing, again, I'm still using the word natural a little bit of a shady way, but at least now we can say, so what would be a hope for a more robust theory of cycles? So it would be an assignment. M goes to some sort of cycle of M. It would be a subvariety of A2C, so this would be an algebraic subvariety. And it would satisfy the property that if I take any A in opt D1, now as I mentioned before, and I'll say it again more explicitly in a second, if I take any A in opt D1, I can define A pullback M in D1 opt. Okay, so the way that this works is, this is a completely general fact about automorphisms of rings, right? If I have a module over a ring, I can take an element of my ring, then apply A or A inverse, depending on how you want to normalize, and then act on the module. So just via, P goes to A of P, and then you let that act on it. So it's a new module over your same ring. And now I should have the property that the cycle of A pullback M is equal to, well now, to A I can associate phi of A, which is an automorphism of A2. And then I want to say that phi of A pulls back cycle. Okay, so a hope for a theory of cycles that fixes these problems would be some way of attaching algebraic variety which satisfies this fundamental relation. Okay, so if you could do that, you would know a lot. I mean, this invariant, whatever it is, if it were to exist, would be pretty refined. So it would fix this Fourier transform problem kind of manifestly, right? So the original problem that I said with the cycles was that if you wanted to compute a Fourier transform of ODEs, you didn't know what they did to singular support. Well, any cycle that satisfied this, sort of by definition, fixes that problem. Because as I said, Fourier transform was supposed to be an automorphism of, it is an automorphism of D1, and the associated automorphism of A2 is just a 90-degree rotation, well, with the sign. But in addition, it also fixes the problem that the cycle wasn't very refined. Because this automorphism group is pretty big. So it's so large that it moves curves in the plane around in lots of different ways. So the first problem we had was that any cycle, it had a very simple form. It was the y-axis and a few vertical lines. Well, if I'm allowed to act on cycles by a big old automorphism group, my cycles are going to be much, much more complicated varieties. So even though this might be more complicated, it will be a very refined invariant by virtue of this equation. So if we had a cycle like this, it would really be telling us some very powerful things about modulus of D. Okay. So this is our sort of best hope for a cycle. Not saying what it is yet, or even if it exists, but that's what I hope for. Okay. All right. So before I start to describe where and when you can do this, let me state the original conjecture in higher dimensions. So this was due to Belov-Kanel and Kontsevich. And this conjecture was, there exists a map phi from the automorphism group of Dn to the automorphism group of A2n. Okay. So these are algebraic automorphisms of a 2n dimensional affine space. And of course, as before, this is not supposed to be surjective, but this is supposed to have the following property, such that phi is onto the subgroup of symplectomorphisms. Okay, so let me pause and say what that means. So, this variety, A2n, is an algebraic symplectic variety. So, this A2n has a symplectic form, which is that if I have coordinates x and y, xi and yi, it's yi dxi. Okay.
D of it.
Oh, sorry, D of this. Thank you. That would be one form, sorry, 22 form. Thank you. Okay. So, so this has a natural non-degenerate 2 form. And what I want are the automorphisms which preserve this form. So for any A in aught A2n, I can of course take A pull back omega, that's another symplectic form, and I demand that of course. So that's a symplectomorphism. It is the analog of the SL2 condition before. So if you look where n is 1 and you just have A2, being a symplectomorphism just means that you have Jacobian 1. In other words, by the same computation kind of that I was talking about before, A pull back of omega in that case is dead of A times. Okay, so to see why you get symplectomorphisms, let me say a word or two about some properties this is supposed to satisfy. So in particular, phi is supposed to take so inside aught of Dn, there's a subgroup which is the linear symplectomorphism group. So this is a group of linear symplectomorphisms. Okay, so just as before, you can see that now how are these linear symplectomorphisms supposed to act? So they're acting on just cx1 plus cxn plus cd1 plus cdn. So, this is a subspace of vector space of dimension 2n. If I take any linear action, any linear automorphism, it'll act on those. And you can check that preserving the symplectic form is the same as inducing a morphism of algebra. So it's kind of the same. I mean, I didn't quite do the exercise before, but it's a pretty simple exercise. Okay? So this group of linear symplectomorphisms acts naturally, and under this automorphism, it's supposed to correspond. Under this map, it's supposed to correspond to the SP, which naturally lives inside here.
It's just, you're saying that it comes from, the inner product comes from the Poisson bracket.
Exactly, yeah, that's right. That's the one line. That's the one. Exactly. Okay. So, these are linear symplectomorphisms, and this subgroup agrees. I'll just finish my sentence. This subgroup agrees with SP2n So that's sort of normalizing things. So that's sort of why the image is supposed to agree with the symplectic morphism. Okay. So, and of course, if this conjecture is true, the best hope for a theory of cycles would have, again, cycle of A pullback M, speed of A. Okay, so this is a conjecture that's supposed to point in the direction of a more refined and better theory of cycles.
But this conjecture doesn't imply that you get this. Right?
No, it
You
does
need
not.
to do much more.
You need to do more. But in fact, if you were to know how to construct a cycle, you would be able to get the conjecture. So let me remark that the two things are interrelated in another way. As you say, this is more than you say it's more, and you're right, it's strictly more. So let's remark that if we know psych, we can get the conjecture. Okay, so why should that be the case? So let's take a in the automorphisms of Dn. Okay, well, I claim that to this A, I can associate an object that I'll call NA, which is a Dn, Dn bimodule. Okay, so again, it's a little bit of non-commutative ring theory, but this is a completely standard procedure. If I have a map of algebras, any endomorphism actually would work. So this NA is equal to Dn as a left module, and then as a right module, I twist the action by A, as the same way I indicated before, or A inverse, depending on how you normalize these things. So, it's twist the action by A. Is A on the right. Okay, so an automorphism now gives me a module, not over my same ring, but over a different ring. No, I think I should just keep going. Yeah, I'll okay, so, but the thing is that, so a Dn bimodule, that's just a module over Dn tensor Dn. But these things are kind of like polynomial rings. So it turns out that Dn tensor, well, technically Dn tensor Dn's opposite ring, but actually none of this matters. D is isomorphic to its own opposite ring, and a polynomial ring in 2n variables with tensor another polynomial ring in 2n variables looks like a polynomial ring in 4n variables. So you can actually, if you just write out a bunch of generators for this and generators for this and sort of smash them together, you can see that that's just D2n. Right? So we can get rid of these bimodules and we can say that for A in aught Dn, I can associate Na in D2n mod. Okay, now, to that I want to associate the cycle of Na. Now again, I don't know what this cycle is, but supposing that there is a good theory of cycles, the cycle of Na is supposed to live now inside A4n, which is A2n cross A2n. Okay? And now, how has this helped us? Well, this cycle is supposed to be the graph of the symplectomorphism from A2n to A2n that I was supposed to get. So this is supposed to be the graph. So this is supposed to be the graph of a map. From A2n to A2n. And in fact, assuming that this theory of cycles satisfies certain formal properties with respect to some tensor product, you can actually deduce that that's the case. Okay, so I won't write out the gory details here, but suffice it to say that, this relation between the automorphism groups is pointing you towards what a cycle should be. On the other hand, a theory of cycles that satisfies nice formal properties will actually yield this conjecture by some completely formal procedure. So the two things are really almost the same. Well, one is strictly stronger than the other, as you point out. But they're very, very close together.
Can you imitate this Dixnier proof to what if you try to imitate that proof to prove the conjecture?
Yeah, you can imitate it, and you will end up with a statement which says something like there is a natural map between tame automorphisms of the Weyl algebra and tame symplectomorphisms of affine space, where tame means in the subgroup generated by the analogs of the ones I wrote down before.
That's a dense subgroup in the topology of uniform convergence.
I would believe that, but it's not everything. Yeah, that's right. So, right. So if you believed that this map was supposed to be continuous with respect to some nice topology, then you would probably win. But I hope to convince you by the end that you should not hope that. At any rate,
because of cycle considerations or the nature of the conjecture itself.
Because certainly with the way that I construct the thing, I would not necessarily hope that that's the case. Yeah, I mean maybe there is a different path which might go through that. But you're right. I mean you're right that they're dense. But yeah, I wouldn't. It turns out that that's not enough to get the full. Yeah, but it works as far as it goes. Okay. All right. So I guess let me state a theorem, and then I'll talk about how to prove it. So here's my piece of paper, and what it says is, suppose A is an ought Dn, then the cycle of this module NA is well defined. And this yields a map from the automorphism group of Dn to the symplectomorphism group of A2n. So this map is onto I don't quite know if it's injective. So this map is onto I don't know if it's injective. So unknown if it's injective. But the induced map from a group that I'm going to call pick Dn to sync A2n is an isomorphism. Alright, so what is this pick? So this pick is a group, which is the group built out of these Dn bimodules, which are invertible under tensor product. So this the set of all Dn bimodules, set of isomorphism classes of them, say, has a monoid structure. You can tensor two of them and get a third. And some objects are invertible in this monoid. I mean, there's a unit which is just Dn as a regular left module and a regular right module. And some objects in this monoid are invertible, and then you get a group out of that. So what I'm really saying is there's a map from ought Dn to pick Dn. That's what this construction is doing for you. It's a morphism of groups. I don't know if it's injective or not, but it exists. And the way my construction works going through cycles, the map from ought to simp factors through this map. So this map is an isomorphism. And I don't know about the original one. So it's sort of hoped that it's the case, but it's not clear. Okay, so it proves that form of the conjecture. Okay, so in the rest of the time I'm going to try to tell you how it works. So how can we construct cycles, at least for some modules, and prove that they give us a nice correspondence between these two groups? So maybe it's worth saying that the injectivity is reduced to the question about this map ought to pick. Maybe it's worth noting that the question is about ought Dn to pick Dn. So in some sense, it sort of forwards this question to the ring theory. I mean, I don't know. I'm not really a hardcore ring theorist, so I don't really know how to answer questions like this. But I feel like, presumably, there's many people out there who do, but it's not. Okay. What's our method? So this is where we sort of leave analysis, I guess, for good. Maybe not completely for good, but at least for a while. So the idea is based on the theory of Weyl algebras and positive characteristic. Over a field K, where the characteristic of K is greater than 0. So in particular, I wrote down some relations for this algebra Dn of C. But if you look at those relations, you'll see it was a ring. The generators were just these formal symbols, and the relations just they were all either 0 or 1. So those relations make sense over any ring or field, right? So just to remind ourselves, we have x and d's, and the relations are things like dixj is delta ij, and all the other things are 0. Just get a larger chunk. Okay, so this makes sense over Z, it makes sense over any. So far so good, but the difference between a Weyl algebra in characteristic 0 and one over a field of positive characteristic is that this algebra now has a very large center. So DNK has a large center. It's a non-commutative ring, but it's really not very far. Centre. I came up with this theorem in Canada, so I'll respect that spelling. So it has a large center, and in particular, its center looks like this. So I'll use Z for the center, as is, I guess, typical ring theory. So of course you have K, and then you have the p powers of all the functions, and then you also have the p powers of all of these differentiation symbols. Right? So if I take any function, if I apply any differentiation to it, if the function's a p power, that'll be 0. And on the other hand, if I take any partial derivative and I do it p times to any function, I'll get 0.
P is the characteristic.
P is the characteristic. Yes, thank you. So, sorry?
So it's exactly equality? So
It's exactly
else?
Yeah, that's right. Because essentially, 1 over n factorial exists if p doesn't divide n. Right? So if you have any other symbols, you can if you just think about functions, any function which isn't in here will be canceled out by some differential operator, as long as it contains a term that has a power that isn't, divisible by p. Okay. So it's a polynomial ring in 2n variables. Honest to goodness. So for these kinds of Weyl algebras, there's a very nice notion of a support cycle. And it satisfies a lot of really nice properties automatically. So let me say that if I take the automorphism group of this ring DNK, there's a natural map to the automorphism group of this A2NK by restriction to the center. Right? If I have an automorphism of a ring, it automatically preserves the center of that ring. So this is just restriction to the center. Okay, so it doesn't require any computations. You don't have to say the word tame. You don't have to write anything out. It's just some completely natural. There's no question that this is natural. Whatever else in this talk may or may not be natural. This thing definitely is.
Can I ask you a question?
Of course.
Before you erase.
Oh.
So NA was a D module over the end. So
NA was a D2N module.
yeah. So what exactly is the statement was saying? So you want side NA sitting inside A to N.
Yeah.
But then how does it use the map?
Oh, how does it yield a map? In the way that I.
But with respect to Gn action on the left or Gn action on the right?
Well,
There
so
are two Gn actions on.
there are two DN actions. So it yields. So the cycle lives inside D. So it's a D2N module. The cycle lives inside A4N, and it's a graph of a map from A2n to A2n. So that's how it works. Yeah. So it's not obvious that it's a graph, but it turns out these cycles, they behave well with respect to some tensor product operations, and you can show that the object that you get is some sort of invertible bimodule over A2n, and so you can deduce that it's a graph. Yeah.
No, and because the way you constructed this, I didn't understand how it follows
Well, I didn't
the
construct
notion
it.
of the map. So if you had an A, then you had this least.
So I have A in ought B Dn.
Yeah.
That goes to NA in D2n naught. And then this goes to psych NA inside A4. Okay. So this turns out to be the graph of a map from A2n to A2n.
Yeah.
Okay. So what was your question?
But so your theorem is about there is a notion of cycle in this particular case.
Yeah.
So cycle was saying that if you take your module and should use an automorphism of your Dn, then you took out another module, and its support
Yes.
agrees with the map.
Yes. So that will follow. That will follow from some tensor product operation. Yeah. So yeah. I am failing to list a few compatibilities, but
And can you remind me what is Dn?
It's the invertible element.
PIC is the group of invertible bimodules. Yeah. That's. Okay. So. All right. So we have some very natural restriction map from this ought to this ought. And so now I can define a cycle. So for M over dnk, I can define the cycle of M, which is just the support cycle of M as a Z dnk module. So in other words, this is a commutative ring. And if I ever have a module over a commutative ring, I can compute its support. So in other words, you take the annihilator in this Z of M. You take the ideal of functions in this center, which annihilate M, and to that ideal you can associate a subvariety or a cycle if you like. It's just in the usual way. I mean, the underlying set of this is just the set of points where this ideal vanishes. So just the usual thing in algebraic geometry. Okay. So let's see this construction in action in characteristic P. So what are some examples? So, for instance, I go to 230, is that right?
No.
Is that true?
No, I have it at 2. Usually.
It might be quite flexible. Usually we make break.
Oh, you guys have an hour and a half seminar? Okay.
We have an hour and a half, but usually we take a break.
Okay. Should I pause or I don't?
I think if you are just flexible about people who might have to leave,
Yeah, I'm
that's
easy.
not because they don't like it.
Yeah. Oh no, it's no problem. I understand. Yeah. Okay. Just keep going and you'll tell me stuff. Okay. I just go till I exhaust myself. Is that fair? Okay. All right. So let's see this thing in action. Let's suppose that I take an ordinary differential equation which looks like v minus f of x. So in other words, my module is just d1k mod d1k times v minus f of x, where f is some polynomial. Okay, so how do I compute this support in this instance? Well, there's kind of a nice formula for it. So you can think of M. So I like to write M in this case as being kx times a formal symbol e. So it's just a rank 1 free module over a polynomial ring, and I have dE is f of x times e. So what I want to do is I want to think about what this module is I want to think about what the action of x to the p and d to the p are on this module. So I want to take d to the p acting on this thing. So if I keep applying d to this thing, what you can show is that d to the p acting on E is f of x to the p plus d by dx acting p minus 1 times on f times E. So, of course, in characteristic 0, there would be lots of terms in between, but all of those terms have p choose I. And in characteristic p, p choose I are 0. So I get some very simple formula like this. Now, even better than that is if f itself is already the derivative of a function. So if f is the derivative of a function already, then p minus 1 derivatives of f are 0. So further, if f is d by dx of g, then this d by dx to the p minus 1 of f is just d by dx to the p of g, and that is 0. So if I have an integrable function on the affine line, this p support is exactly, so to m, I associate the equation d to the p minus f to the p plus d by dx. It's 1 of f, and if f is integrable, I get d to the p minus f. So some extremely simple equation, which just drops sort of directly out of the defining equation of n. And notice also now that these supports are essentially all different for different f's. So all of these different rank 1 modules, if you just look at their support in the d to the p, x to the p plane, they're all graphs of the different functions, right? So these are it's sort of a very fine invariant that distinguishes lots of different things. And furthermore, this invariant is completely natural with respect to these transformations here. So if I take this restriction to the center automorphism, let's again call it phi, I didn't give it a name before, I certainly do have that the cycle of A pullback M is equal phi of A inverse acting on the cycle of M. So that equation, which was so elusive in characteristic 0, here in characteristic P it's completely automatic. And the reason is that it just drops out quite directly from the definition of support. So the support of a module is just its support over some ring, and if I act by an automorphism on that ring, the automorphism of the module will move the support the same way. So it's just sort of completely tautological. So we see that you sort of get both of the things that you would have hoped for. You get a very powerful invariant that's telling apart lots of different modules in a nice way, and it's also completely natural. Okay, so that's the theory in characteristic P. So now the goal is to sort of reconcile these two things. We know there's a good theory in characteristic P. We hope there's a good theory in characteristic 0, but, why should one imply the other? I mean, they're just different worlds. So how can you go from characteristic P to characteristic 0, and what would that mean? So, let's write down some definitions. Let's see if they make any sense. So let's take M, a DNC module. Okay, well, and let's suppose, I guess I haven't really been using this word much, but let's suppose that M is finitely generated. Okay, well, M has finitely many generators and relations. Now, all of those generators and relations are just polynomial differential operators over the complex numbers. Okay, so it could be complicated, but it's certainly the case that whatever these generators and relations are, they only involve finitely many numbers. So these generators and relations, they involve some complex numbers, but there's just finitely many complex numbers. And so this means that this M is defined, it makes sense over a ring which is finitely generated over the integers. Okay, I take the integers, I join finitely many complex numbers. Some of them could be transcendental numbers, some of them could be algebraic, but it doesn't matter. There's some nice ring out there which contains all the coefficients you need to define the equations which define M. And they make sense over some finite ring like this. Let's call this ring R. I didn't give it a name. Okay. Now since this R is finitely generated over Z, I can take the reduction mod P of R. So I can take R mod P for all but finitely many primes P. Right, so this R might involve some rational numbers like 1/2 or 1/3 or something, but it only involves finitely many. So for all but finitely many primes, P is not a unit in R. It defines some prime ideal, and so I can take the reduction. Okay, so starting from a D module, Dn module in characteristic 0, I can attach an object in characteristic P. Right, so we can take, so let's denote MR, where we just take M, but we consider it only as a module over the ring, polynomial differential operator over the ring R. So denote MR, the Dn R module, I want to say it becomes MC. In other words, when I take a tensor product over R with the whole complex numbers, I just get the original M back. That's the technical notation. But the non-technical way is just to think of M as being defined over this ring R. And then we can take MR mod P, and this is a Dn R mod P. Now,
so it doesn't matter the coefficients being a field or not.
Sorry?
It doesn't matter the coefficients being a field or not.
Which field?
I mean, in your previous selection, you had a DNK module where K is a field of characters.
I had K was a field. That's right. So in general, this will be for P large. This will be like a domain or something, and then I have to take its field fractions. That's right. So this DNR mod P, I can then base change this to DNK, where K is like the field of fractions of R mod P. That's absolutely right. I do have to do that. Yeah, absolutely. Okay. So I take MR mod P, after maybe adjoining some fractions, I end up with a module over DNK, and this makes sense for any sufficiently large prime. So then what can I say? Well, to each one of these DNK modules I can attach a cycle. In the way that I said before. I just take this support. But the problem is now that it's completely unclear that I get any kind of manageable or well-defined thing. Right? I take a module, I reduce it mod P. In each mod P, I look at the center, and I take the annihilator of this module in that center. Okay, so it's infinitely many ideals in infinitely many rings over infinitely many different characteristics. So, a priori, it looks like a big mess. So, let's make a definition. We say that the cycle of M is defined if what happens? Well, if there exists some variety L inside A2 and C, a variety, such that, so this L exists in characteristic 0, but now I can play the same game with L that I just played with M. In other words, I can define L over some finite type ring R, and I can take the reduction mod P of L, right? So such that if I take L, if we take the reduction, L R mod P, or let's even say LK with characteristic of K greater than 0, then we demand that the cycle of M is equal to this L. Then cycle of MK is supposed to be equal to LK. Okay? So I'm not saying it is defined necessarily. I'm just saying it could be defined. And it is defined if there is a variety such that whenever I take its reduction on P of that variety, for P very large, it will agree with this symbol.
So do you want LC to be defined over integers?
No. So it turns out that the ring doesn't matter. So this condition is independent of the finite type ring over which everything exists. So that's a little bit hard to see, but that's true. So it doesn't matter. So we take LC, that's coming from LR, and this LR is going down to LK. But it turns out this R, so you demand this sort of for all R, but it turns out that it doesn't matter. If it's true for one R, it's sort of true for all of them. Okay, so the R doesn't, so R sort of doesn't matter. R doesn't actually matter. So it's sort of a prop that you use to sort of go from one world to the other, but the ultimate definition ends up being independent of the model. So it really only depends on the module in characteristic 0. It turns out to be a completely well-defined notion. Okay, so now let's restate the theorem from before in this more precise way. So now the theorem is going to read as follows. Let M in pick of Dn, so it's an invertible Dn bimodule, then psych M is defined. In the sense that I just made here. So the reduction mod P of it is a uniformly defined thing, and it equals L, which is the graph of a symplectomorphism. The graph of a symplectomorphism. Okay? So it's defined, and it equals the graph of some symplectomorphism, and that's the map from pick to the symplectomorphism group. And now let me state another theorem, which is in a sense even more general. So theorem 2. So this is my sort of just restatement of the way that I stated the theorem before. So now let me state theorem 2. So now we go the other way. Now we let L inside A2n be so a subvariety which is isomorphic as a variety to an. So you take some embedding of an into A2n such that L is Lagrangian. Okay, I haven't used that terminology yet. But suffice it to say that if I take a symplectomorphism of A2n, then its graph in A4n is a Lagrangian subvariety. So these graphs of symplectomorphisms are examples of half-dimensional Lagrangian subvarieties, which are isomorphic to an. So this is a generalization of the previous thing. Then there exists a unique Dn module M, such that the cycle of M is equal to M. So there's a surjectivity property as well, which I mentioned before. So in the automorphism world, this means that if you take the graph of any symplectomorphism, you can find a unique bimodule whose cycle is equal to that.
And does it have to be invertible?
It will be, yes. If this is a symplectomorphism, that will be invertible. So these things are compatible with various tensor product-like constructions, and so you can see that that's true. In other words, if I take the graph of a symplectomorphism, I compose it with its inverse, I get the diagonal. So So you take these two associated unique things, when they tensor, they'll be the unique thing which lifts the diagonal, which is the triple.
But in this case, when L isn't a quadratic graph of automorphism, you can still get this M.
You still get M, yeah, that's right. But it
Doesn't have to be inverted.
Well, it doesn't even have to be a bimodule. It could just be a module over some n, where n is any number.
I see.
So if n is an even number, then you can ask if it's an invertible bimodule, and then that's true if and only if the associated thing is a graph. Yeah. So it's quite a bit more general, actually. Yeah. Okay. So those two theorems imply the conjecture of Belov-Kanel and M that I wrote down. So to any simple automorphism, there's a unique element of pick, and so ought maps to simp as a surjective well-defined. Okay. So, all right. Not quite out of gas yet, but I feel like it's getting pretty long. So let me just indicate in the last few minutes how the proofs of these theorems go. So, so the proofs of these things are via lifting and rigidity methods. So the proofs, so I use a lifting method and a rigidity method. Okay, so for the first step, we have the following sort of issue. Let's suppose that I take some LC inside A2NC, a Lagrangian, and L is isomorphic to AN. Okay, now I can reduce this L mod P for P very large. So from here I can get LK inside A2NK. And to this LK I want to associate an MK such that the cycle of MK is equal to LK. Okay, so for instance, let's go back to the very first example of a graph of a function. Right, so let's say I take n equals 1, and let's say I take this Lagrangian subvariety y equals f of x. Okay, so this is just graph of some function, so it's certainly a Lagrangian subvariety of A2 isomorphic to A1, right? So this is inside A2. So this is a copy of the line. Maybe I should say y minus f of x, but whatever. No, actually y minus. All right. So to this thing I'm going to associate m is equal to the module d1. I want d1 times d minus f of x. So I claim that this y minus f of x just goes to d minus f of x. So this comports well with what I said before. So let's see why that's true by characteristic P techniques. So we computed already that the support of this m, when I reduce it mod P, right? So now f of x is in characteristic 0, but as long as the, you can imagine f being defined over some ring, as before, you can reduce the coefficients of that ring mod P, and now you can take the support of this reduced m, and so, as I said before, the support of that thing is going to be d to the p minus f to the p plus this d by dx to the p minus 1 of f. And this part was 0 as long as p is large enough. Right? So if p is very large, this is a p derivatives of some g. And so this is 0 as long as p is large. So I'll actually just not create more work for myself and write. This is just d to the p minus f to the p. So now in the affine plane defined by the coordinates d to the p and x to the p, this is just y minus f of x. Right? So this thing, by sort of 1 over p-ing everything, is just y minus f of x again. So in this example, we see that the support of this module is defined in the sense that I said before. And it's completely independent of the ring. You take any ring, you reduce mod p, you embed the coefficients into some field, and as long as p is large enough with respect to this polynomial f, namely all of the powers of f, the n's that occur in f are invertible in p, so you can integrate, you will get that this is your support module, your support thing. So this cycle is well defined, and it gives you this equation. Okay, so let me return to the general case just briefly. So for a random L inside A2n, how can you come up with something inside in characteristic P? Well, so what you end up doing is you can show, so maybe the best way to say it is this. So to construct MK, in general, essentially, you use a theorem in non-commutative algebra. So you use the fact that D of A and K, which I'm just calling DNK, sorry, is automorphism over the center. Okay, so essentially, this is a fact from non-commutative algebra that means that this Dn is almost like a matrix algebra over its polynomial between two variables. And so, essentially, what I can do is I can do sort of something that looks a lot like this sort of explicit computation to prove that this Azamaya algebra is what's called split on L. So it turns out that, so using a very similar computation, so it's similar to this one for graphs, but a little more difficult. You can show that Dn is split on Lk. So what this means is that when you restrict Dn to this subvariety, it really is a matrix algebra. And so there's a canonical module, which is just corresponding to O of Lk. So this yields Mk. So this yields a canonical Mk. Okay, so this is a little bit of a long-winded way of saying that to construct a correspondence in characteristic P is not very difficult. You just use non-commutative algebra techniques from the theory of D modules in characteristic P, and maybe a little bit of computation. So the real key idea in the paper is that you want to lift. So you want to lift Mk to some sort of M, which lives over a ring in characteristic 0. So I'm going to write wit ring of K. If K is a finite field, this wit ring is just like a ring of p-adic integers. Right? So if I had M over Fp, I would want to lift Mk to M over Zp, for instance. So e.g., Wk equals Zp if K is Fp. Okay, and so in order to do this lifting theory, I develop a theory of deformations for Dn modules in positive characteristic. So the sort of highlight here is that you need deformation theory. So you need deformation theory. So you use deformation theory for Dn modules. Use it, and I sort of develop it in the paper. And essentially, the fact that this Lagrangian that we started with is isomorphic to An means that this deformation theory is very well behaved. So you start with an L, you construct this Mk, which is like almost equal to L, not quite, but there's a little bit of non-commutative algebra, but it's supported on this smooth affine space, and then the cohomology of smooth affine space is very easy to compute. It's not 0 in characteristic P, but nonetheless you can handle it. And so so using the fact that Lk is isomorphic to An, you can show that there exists preferred deformations. So there exists a preferred lift. And then the final step is to use rigidity in characteristic 0. So even if I construct all these different lifts, what these essentially are doing is constructing all different modules which live like over different p-adic fields. But I want a module that just lives over one field. I want to show that they're all the same. So as it turns out, these M that you get have a very special property. So these M that you get, these MWK, are actually rigid D modules. So they satisfy that they have no self-extensions. And it turns out that any D module like this that have no self-extensions is essentially unique. It's not that there's only one in the whole world, but there's only one that satisfies certain behavior at infinity. And so what you can show is that all of these different modules over different fields of characteristic 0 are the one rigid D module that satisfies some certain condition, and so therefore they have to all be essentially isomorphic over some smaller field. Okay, so that was a little rushed at the end, but I think I'm almost at my time. I should probably stop.
Let's say if a cycle is defined for some module, then what do they correspond to under Riemann-Hilbert correspondence?
Well, almost all of these D modules will have irregular singularities.
Oh, you're right. I see.
Right? Because so like the primary example is like D minus f of x, where f is a non-trivial function on the line. So at infinity they'll all be irregular. Yeah. So unfortunately they don't really fit into that scheme. Yeah.
Questions? Let's.
Well,